Hey guys, today we're going to do partition labels. So this is just another greedy problem. So basically what the problem states is that you're given string S, we want to partition the string into as many parts as possible so that each letter appears in at most one part. For example, ABABCC can be partitioned to ABABCC, but partitions such as ABAB, or sorry, ABA and BCC or ABABCC are invalid. This is because we basically want to, for every element that we have in the string, we want to partition them such that they only exist in one of the partitions, basically. Right? And the goal is to partition the string into as many parts as possible. So this already hints or alludes to the use of greedy. And basically what we're trying to do here is return a list of integers representing the size of these parts. So let me just add one more test case here. Q, R, S, T, U, V, W, X, Y, and Z. So let's say for this example, I'm just listing out the alphabet. What they're expecting is, sorry, and I guess let's add one more here where we repeat A. Right? So basically what they're expecting us to do is, so here you see we're having 26 unique characters and we want to partition them as small as possible. So technically this entire string can just be as is. It can be returned and it's one partition, but we want to partition it into as many parts as possible. Therefore we split this into A, comma B, comma C. You get the gist basically. And what if we have an A at the end? What if we append an A? We see here we return one partition only of 27 characters. So we can imagine this as being, let's say we have A, B, C. A, B, C, C, right? So we can imagine this as just having this here. Or, sorry. This and this is another partition. And so how do we determine this in a way such that we know for sure that the characters inside each partition are only contained within that partition? The approach I thought of was actually just going through it by one pass, but this is actually extremely difficult to do with like a one pass thing. So basically, like, think about it this way, right? If we do something like A, B, C, D, E, F, G, H, I, J, K, L, H, I, J, K, L, M, N, O, P, Q, R, S, T, U, V, W, X, Y, and Z. If we do something like this, let me get the font larger. If we do something like this, if we go through this at one pass, okay, I mean, we can make a partition here, we can make one here, we can make one here, but what happens if, say, the string suddenly has another A at the back, or another, sorry, okay, we can't edit that? Cool. What if it has another A at the back here, right? So all of a sudden we can't do these partitions anymore, right? We can't do these partitions. We have to just combine them into one partition, as I've shown just now, right? So instead of having these, we now have to separate them, or we can't separate them anymore. We have to have this entire array, this entire string into one partition, right? Just because of this one A at the end. So it's very difficult to do this in one pass, but it is possible through the greedy to do it in in linear time, so O of n. The solution basically is just taking the last occurrences of each character. So let's see, we have, this is a pretty good example here. So if we have this string right here, right? the way we approach this is basically we want to find what's the last occurrence of A, what's the last occurrence of B, A, B, and so on, right? And basically, what we're trying to do is we're trying to extend the, think of it as sort of like intervals, right? So this is our current interval, and we iterate B, okay, B is here. Looks like B, the end of B is within the end of A, right? Because this is the end of B. So end of B is within end of A, so we can simply erase this and extend our interval to cover A and B. And then we go to A again. Okay, we still have that. We append this into the interval, and so on until we reach a new element. Okay, C. What is the last element in C? It's this one. The index here is still less than A. So we know this also is included within the interval until we reach the end of the interval, right? So basically what we're doing here is we're checking for each element, is the last element, so here the last element is here, so we extend it, right? Is the last element of each character greater than or less than the the greatest last element, essentially, right? So B is here, A is here, C is here, right? B here, its greatest last element is still smaller than A. C here, its greatest element, or its final element is still less than A. So basically we can just anchor it on this one. So we know that once we reach our I is equal to the greatest, which is this A right here, then we can end our partition, right? Because we keep on checking for when the partition is still expanding or has it reached its maximum end. So basically, we can just think of it as always keeping a maximum end. So here is max end. Always checking for when our max end is equal to what our index is, right? So if A's max end is here, this is max end, then obviously we're going to keep on expanding our partition, right? A's max end is here, so we add that to the partition. We add this to the partition, right? B, what's its end? What's the final element of B? What's the last index of B? It's in index 1. It's smaller than A, so obviously we expand it. C, what's its last index? Well, 2. Definitely not as large as A, so we keep on expanding until we reach the maximum end, right? And what if we find, like, let's say there's a Z here, right? So if there's a Z here, the moment we're trying to iterate before A, we suddenly update our max end, right? Because we've encountered a max end that is greater than our current one. So this one in Z is greater than this one in A, right? Then we expand it, right? We automatically expand all the way to reach Z. And we could just keep on maintaining that logic throughout the entire string. So even if we have like a very extremely long string, where suddenly before the last index we find that there's a greater max end, then okay, we just need to set the current max as that new max, and then okay, we check here, does I equal to the new end? If it doesn't here, right? Because we've already updated it, then okay, then we're gonna keep on expanding it basically until we reach the maximum end. It's the same principle as jump game, basically. We're just going to keep on expanding, keep on trying to find the maximum end. So I guess with these sort of questions, we just need to figure out where is the max end, right? And so that's basically the intuition for this question. Now we're going to try and code it up. So firstly, we're going to make a frequency table, right? Or sorry, not a frequency table, a end of index table. So we can write here char ends, or let's just say ends. Ends is a dictionary. So for char in S, ends char equals to, oh, let's just do a, oops, for I in range, when s char, or ends char I is equal to, sorry, ends si is equal to the index. So here we just verify that this is proper. Yep. So as you can see here, right, this is the current end, or this is the end of each letter in the current string, right? Yeah. So basically, what we're gonna do is let's use our loop invariant, right? Or sorry, we can just iterate through the entire. We can iterate through the entire string here, and we maintain that the end is equal to, the max end is equal to max of our current max end, and let's just say this is 0 for now. And let's keep our end is equal to ends si, and, or we can just do this actually, this is much better, si, right? So max is the maximum end that we currently have for each character. So for the character of si, or I think we should just simplify this to make it much easier to understand. So for the current char, let's do current char. So for the current character that we're iterating through, what's the max end that we can find? Here it's 8, right? And so basically we just keep on updating the max end until we find that the current index that we're iterating over is equal to the max end. And in this case, we found our result basically, or we found one of the results. So we just simply need to res.append, and this should be the current index we're in, so I. And we then simply reset the max end equals to 0. And here we return the res, essentially, right? Yeah, so we basically keep on checking for each index, is it the maximum end? If, oh, we should actually put this at the end instead of the start, because we're going to overwrite max end. Yeah, so we keep on checking for each index. Once we reach the one that equals to max end, we append it into the result. So here it's 0, 1, 2, 3, 4, 5, 6, 7, 8. We append 8 into the result. Although the answer requires 9. Note that the partition. Oh, okay. So we should actually do this. Sorry, we should do end my. Okay, sorry. We should have one more variable actually, which is start. Start equals to end equals to 0. And end should just be current char. And here we should do end minus start is equal, or end minus start plus 1. And here we just reset the start is equal to n plus 1, because as I've said, we basically start the new partition here once we find that the end is valid. So yeah, I actually had to re-record this because the recording stopped, but yeah, I just resubmit this. This is the solution for 763 partition labels. Yep, thanks.